So at this point, we're finally ready to start tackling some problems. And what I need to do here is review. We need to review right triangle trigonometry. So again, that basically refers to SOHCAHTOA. So I'm assuming for the most part that you remember this, and I did mention in the previous video this idea that the sine of an angle is equal to the opposite side over the hypotenuse. The cosine of an angle is equal to the adjacent side over the hypotenuse, and the tangent of an angle is equal to the opposite side over the adjacent side. Keep in mind these three ratios, these can only be used in right triangles. Sorry, not 90 degrees, 90 degrees. So if you have a triangle that has a 90-degree angle, you may use SOHCAHTOA. If the triangle is not a right triangle, you cannot use SOHCAHTOA. You can use sine, cosine, and tangent in other ways, and in some videos that are coming up, we're going to learn about some ways of solving triangles that are not right triangles. But the business of SOHCAHTOA can only be done in right triangles. So I've got sort of 4 examples coming up, 2 that are very basic, and then 2 that are a little bit more interesting. So we'll get to those now. You are going to need a calculator for these, so hopefully you've got a calculator around. If not, use Google. Seriously. Alright, so my first example, find the values of x and y in this triangle. First thing to notice, or to note here, the angle that I gave you is in degrees. If you have an angle that's in degrees, your calculator needs to be in degree mode. And that's something you may not have ever paid attention to before because everything was always in degrees. But now that we have both degrees and radians, we need to be mindful of that. So if you're using a TI 83, 84, Inspire, any of those, there should be a mode button on the calculator. It's in the upper left-hand corner right next to the second button. If you hit mode, you'll notice on the third line down, it says radian and degree. That is precisely how you change between modes. You just use the arrow keys, pick the one you want, and hit enter. So for this problem, we're going to need to be in degree mode. So we pick degree, and then we quit back to our home screen. So let's target getting x first. If I want to find x, the idea is, and if you already know how to do this, like set this up on your own, make sure you've got it, and then just check your answer with the video. From 73 degrees, the sides I'm looking at here are the opposite side and the adjacent side. Well, the ratio that has to do with that is tangent. So we would look at the tangent of 73 degrees is equal to the opposite side, which is 21, over the adjacent side, which is x. Right? As far as solving this is concerned, we'll multiply the x to the other side, get x tangent 73 degrees equals 21, and then we'll divide that tangent 73 degrees over. X equals 21 over the tangent of 73 degrees. At this point, we can go to the calculator. We put in 21 divided by the tangent of 73 degrees. This ends up being 6.42. You're going to hear me say this a lot. It is now worth thinking about whether that answer makes sense. Right? Your drawing might not be to scale, but keep in mind, if this is a 73-degree angle, then this guy over here, these have to add up to 90, this has to be 17 degrees. X is going to be significantly smaller than 21, so 6.42 is a reasonable answer. Okay? So now how can we get y? Well, one of the options is to use the Pythagorean theorem, so you could certainly do 6.42 squared plus 21 squared equals y squared in square root, or we could use this as an opportunity to practice more trig, which is what I'd like to do. So with that in mind, what trig ratio should we use? I'm of the opinion that the best bet is sine, because we know the opposite side, it's 21, and the hypotenuse is what we want to find. Right? You could have used cosine because now we do know x, but personally I always like to go with sides that were given to me in the problem because it means I don't have the chance to mess up. Right? I get to use values that were already given to me. Right? So the sine of 73 degrees is the opposite side, 21, over the hypotenuse, which is y. We're going to do the same thing we did in the previous problem. In fact, I'm even going to skip that step and just say y is 21 over the sine of 73 degrees. And when we solve this one, we will end up with 21.959. So it's actually like 960. And so this is our hypotenuse. Right? Again, it it's worth it to take a moment and see if this makes sense, right? 21.960, it's bigger than 21, so at least it's in the realm of possible, okay? So let's go on and take a look at the next example. So in this one, I want us to find the value of x in this triangle given below. This time you'll notice that the angle does not have a degree measurement on that. On top of that, it's a ridiculously small angle. If that was a degree measurement, like imagine how small 0.54 degrees is. It's incredibly small, and that's possible. I mean, if I'd put a little degree symbol here, then that's what I would have meant. But the reality is, if you're ever working with an angle that's a very small number, more than likely it's going to be in radians. Keep in mind that degrees, you've got 360 of them in a circle, whereas with radians, you've got like 6 radians in one circle, as opposed to 360 of them. Radians are much smaller numbers. So before you do this problem, remember to go into your mode and switch it over to radian mode. Once you've done that, everybody should be able to do this problem on their own. So pause the video to do that on your own. You should have set up the idea that the cosine of 0.54 radians, oops, I'm sorry, not the cosine. That's the opposite side, so that's actually the sine. The sine of 0.54 radians is 4 over x. So just like we did last time, we can move stuff around. X equals 4 over the sine of 0.54. So that means x is equal to 4 divided by sine 0.54. I'm getting 7.780. So that's what I get for x. And again, does that answer make sense? I mean, at least it's bigger than 4. The hypotenuse should be longer than 4. So that answer at least seems within the realm of possibility for us. Okay. Next problem. Find the values of x and theta in the triangle below. So in this problem, it's not indicated whether the problem is radians or degrees. And if the problem doesn't indicate, then it doesn't matter. Like it's not significant. Your calculator can be in radian or degree mode. But no, when you go to solve for theta, like when you go to actually find out what that is, if your calculator's in radian mode, the answer you get back is radians. When you go to solve for theta, if your calculator's in degree mode, then the answer you get back is in degrees. So just be aware of that when you're doing the problems. At the moment, everybody's calculator's in radian mode, so leave your calculator in radian mode. Let's stay there, right? So how are we going to find x and theta here? Well, there are a number of different options here. I mean, one of them, not a good one, but one of them would be to use the sine. The sine of theta would be equal to x over 5. But the thing that's frustrating about that is that there are multiple variables here. There's theta and x in the problem, so I can't really solve for the thing. I think the better bet would probably be to use tangent. And what I'd recommend you do now is pause the video, set up tangent, and look at why tangent made more sense, or maybe even think about why it would make more sense. So what we find is that when we do tangent, we have the tangent of the unknown angle is equal to the opposite side, which is x, divided by the adjacent side, which is 3x. Right? In other words, the tangent of the angle is 1/3. And I almost want to take a second here and say, we mentioned before that with these trig functions, you're plugging an angle and you're getting back a ratio. Even though I don't know what these two sides are, the ratio of these two sides is clearly a 1/3 ratio. X over 3x will give you 1/3, and because of that we can actually solve this thing to figure out what it is. Right? So now this next part could be kind of hazy for you from your geometry days, but the idea is I now have a trig statement. Right? This is saying that the tangent of some unknown angle is 1/3. So how can I find that unknown angle? I can do that by using inverse trig functions. I can say, okay, the angle I'm looking for will be the inverse tangent of 1/3. Okay? Now on your calculator, the inverse tangent button is usually right above tangent. So on a TI calculator, it'll be second tangent. So if we go second tangent 1/3 and hit enter, it'll come back and tell us, hey, that angle you just found was 0.322. And we take a moment to ask ourselves, is that angle reasonable? And remember, this is a radian measurement. Like, this is radians. So there's a sense in which we even need to take a second and think about what that is. And I'm hoping that you guys have at least a little bit memorized the radian values that we had from earlier. Remember, the smallest radian value I had you guys memorize was that 30 degrees is the same thing as pi over 6, which is, about 0.5. So when we get a radian measurement of 0.3 radians, like, what's an estimate for that angle? An estimate for that angle should be something like, like 20 degrees-ish. Is that reasonable in this problem? Is theta being 20 degrees reasonable? It seems like it's okay to me. If this side here really is 3 times longer than this side, you have a fairly small angle here. Okay. At this point I want us to actually find out what x is. So now that we want to find x, we're actually going to bring this information back to the problem. I wasn't expecting this, but it turns out this sine thing is actually now really, really useful. Now that we have an angle for this thing, we can go back and do it. We can say that the sine of 0.322 is equal to x over 5. In other words, x is equal to 5 times the sine of 0.322. Now, stop. Before you punch that in your calculator, and this is going to be huge moving forward in math, if you ever got an answer from before, please don't ever type this into your calculator. Like, I hope you didn't take your calculator and type 5 sine 0.322. On your calculators, there's an answer button. It's on the TI calculators. It's right next to the enter button, right above the negative button. There's a little ANS thing. On your calculator, what I want you to actually type is 5 sine parentheses answer button. And what that does is it takes the previous answer you got and pastes it in all of its 10 digits. In fact, the calculator actually stores more than 10 digits. It actually stores the exact whole thing. So if you punch that into your calculator, you'll come back with 1.581, which is sort of the most accurate possible value that we can get for this. Okay. Again, we get that answer. We think about whether it makes sense. It means this side here is about 1.6. It means this one over here is 3 times that, so like 4.8-ish. That's less than 5. Seems good to me. Now, before I go on to my last problem, I want to point out to you, this was a problem that had 2 variables. Very, very often when there are 2 variables in a problem, you have to solve the problem by setting up a system of equations. In other words, setting up one equation and either solving it to plug into another, or sometimes setting up 2 equations at the same time and using some sort of a substitution thing to work through them. I think we're going to see that happen in our next problem. So this last example that I have is a somewhat more complicated example. If you're feeling really good about all this stuff, in fact, I'd really like everybody to try this problem on their own. I do want us to set it up together first. So if you want to try it on your own, draw the picture of the thing and then watch the video to make sure you have the diagram set up properly, and then feel free to try it on your own. So you've got the idea that a student is walking towards a flagpole. Okay, so let me draw a flagpole. I'm a really good artist. So here's a flagpole. A student's walking towards it. At a certain distance away from the pole, the angle of elevation... I want it to be a taller flagpole. There we go. At a certain distance away from the pole, the angle of elevation is found to be 20 degrees. That doesn't look like 20 degrees. The angle of elevation... Let's try again. So the idea is at some point way over here, they find it's a 20-degree angle looking up to the top of the flagpole. Then, after they walk 45 meters closer, the angle of elevation is found to be 70 degrees. So, they started out here. Now they're over here, 45 meters closer. And now, we'll deal with it. Now this angle of elevation is 70 degrees. And the question is, what is the height of the flagpole? That's the variable that we need to find. And this is a right angle here, of course. So that's the setup for the problem. If you had that set up on your own, great, awesome. At this point, I want you guys to use right triangle trigonometry to solve this problem, to figure out what the height of that flagpole is. If you feel up to it on your own, go for it. If you need some hints, I'll give you some hints that may unravel things along the way. But please try and do as much of this on your own as possible. So the first hint that I would give, if you need one, is we need to do some right triangle trigonometry, which means we kind of need some multiple sides here to work with. And so I'm thinking, like I see a triangle here that I'd like to work with. I need multiple sides though, so I'm going to take this distance here and give it some other name. For instance, if we call this y, I now have a triangle that has sides of x and y with an angle. Right? So that's one right triangle, dot, dot, dot. If you think that's enough for you, then go through the problem on your own. If you need another hint, the idea is here is another right triangle. In this right triangle, what are the dimensions? The dimensions are x for the height and y plus 45 for the width. So with that information, I'm hoping that you guys can work through this and do some stuff. So with this one, I'm going to start solving the problem. I'm really hoping you guys have done something on your own. From the smaller triangle, from this guy here, we have the relationship that the tangent of 70 degrees is equal to the opposite x over the hypotenuse of y. Right? From the larger triangle, from the 20-degree triangle, sorry that was a messy tracing, we have that the tangent of 20 degrees is equal to the opposite side, which is x, over the adjacent side, which is y plus 45. Okay? You'll notice at this point, neither one of these equations is solvable. Both of them have multiple variables in them, which means we're going to have to use something like substitution or elimination to solve them. If you haven't been able to do this up to this point, pause the video, see if you can figure out what to do next. From my perspective, I see this as x equals y times the tangent of 70 degrees. And on the other one, I get x, I should use red for this. So x equals, let's see here, the tangent of 20 degrees times y plus 45. And I mentioned in the previous, like right at the end of the previous problem, that sometimes you're going to have things like this that are going to sort of be a system of equations. We now have two equations that have x and y in them. They're both equal to x, which means we should be able to set both of these things equal to one another and then solve for y. There's going to be some numbers to work through, there's going to be some algebra to do, but if you're getting ready for calculus, you're ready to move ahead of these things, something like this should not be overly challenging. So pause the video, set those things equal to one another, you use your calculator and actually fight through this. Alright, so here we go with actually solving this. So we'll have y tangent 70 degrees equals, and if I sort of distribute this through, you'll have y tangent 20 degrees plus 45 times the tangent of 20 degrees. And something I like to remind people of here is your job is to solve for y, right? Tangent of 70 is just a number. Tangent of 20 is just a number. Like if this had been 3y and this had been 5y, no one would have even thought twice about just subtracting that over. So the idea is this thing will be brought over this way. I'm going to have y tangent 70 minus y tangent 20 is equal to 45 tangent 20. And then on the left side I can actually factor out the y. So you get y tangent 70 minus tangent 20 equals 45 tangent 20. And then the final step that we can take is sort of dividing that thing over. So I end up with y equals 45 times the tangent of 20 divided by the tangent of 70 minus the tangent of 20. At this point we can plug all this into our calculator and see what we get for y. I ended up getting that this was 6.872. Remember, these are degrees now, so your calculator needs to be back in degree mode. So that's my y value. To find the x value, we just grab one of these guys here and plug into it. We're going to get the x is equal to that thing, 6.872 times the tangent of 70. So if I plug that in, times tangent 70, I end up with 18.880. And those are our values for x and y. Keep in mind, the question actually asked what the height of the flagpole was, and if my memory serves me, that was in my diagram, that was x. Yep. So the actual answer to the question, the thing that we were actually supposed to solve for, is this number of meters. It's 18.880 meters tall. I know this entire video is on the long side. A lot of it should have been review. At this point, if you've got some energy left, you might download the assignment and try some of the problems. Just give these a shot and make sure that you're getting not just the basic ones, but also the more advanced ones like this.